All right, perfect. Man, when you picked up a marker. Oh, you gotta be kidding me.
Is that the only marker?
No. Something else. The cap is like off. It was one that I grabbed that was new, but a kid got access to my backpack and took the cap off. I didn't know how long it was off, but it looked like it should dried out. So marker's gonna suck today, which is too bad. Anyways, so today we are starting with loci and sets. Now, before we get into loci, let's just go over, this is probably review of set theory for a bunch of you guys, but if not, let's just review basic set theory. So first off, what is a set? How many of you guys have done math with sets before? You've done math with sets? What's a set? A set is an unordered, unique collection of objects. And we typically put it between two curly braces like this, the objects inside a set. So let's go over what I mean by unique and unordered. I mean that set is the same as this set, so order doesn't matter. It is the same as this set, meaning duplicates don't matter. So it's a unique, unordered collection of objects. All three of these sets are the exact same set. And it doesn't matter what you put in a set. I happen to have these sets full of numbers, but I can put anything I want in a set. It's just a unique, unordered collection of, we typically say objects, but of whatever you want to put in there. Objects, just the most generic word we can think of. So that's all a set is. You good so far? Mm-hmm. So, let's go over some operations we can perform with sets. We have the idea of the union of two sets and the intersection of two sets. So let me create two sets real quick. I'll say A is equal to the set 1, 2, 3. I'll say B is equal to the set 3, 4, 5. So one of the ideas that we have is the idea of a union of two sets. So if I have A union B, union is this symbol right here. A union B, that produces the set that contains everything that's in this set or in this set. So in this case, it's 1, 2, 3, 4, 5. Good? That's the union of A and B, right? Mm-hmm. The intersection, A intersect B, is equal to the set of everything that's in A and in B. So what elements are in A and B?
3.
3 is the only one. So that just leaves us the number 3. That's the only thing that's in both those sets. That is very unreadable. Jeez. Oh. That green works okay, right? So that's the idea of union and intersection. We have another idea of subset. A is a subset of B, means that everything that's in A is also in B. So let me set up a scenario real quick. A is 1, 2, 3, B will make 1, 2, 3, 4. In this case, we would say that A is a subset of B. That's our subset symbol in some books. Some books just use it like that. And I won't go over the idea of a proper subset. We don't really need to know right now. So for right now, I'll just use this symbol for a subset. A is a subset of B. What do we mean by A is a subset of B? We mean everything that's in A is also in B. Does that make sense? Question. Is A a subset of A?
Yes.
Yes, everything that's in A is also in A. So A is a subset of A. That's always true. Doesn't matter what set you're talking about, right? Okay. So one of the ways that we show that two sets are equal is we show that if A is a subset of B and B is a subset of A, then those two sets are equal. If everything that's in A is in B and everything that's in B is in A, then the two sets are equal. Does that make sense? So that's a common strategy for showing that two sets are equal. In this case, are the two sets equal?
No.
No. Everything that's in A is in B, but everything that's in B is not in A. A is a subset of B, but B is not a subset of A. Now, if I do that, A is a subset of B and B is a subset of A, therefore they're the same set. So that's how we show that two sets are equal. That's a common way to show that they're equal. Let's see. What's some other basic set stuff I wanted to go over first? Set builder notation is one more thing. So if I say that A is equal to the set of all, we put some dummy variable. So X, when we put it here, we call this a dummy variable, and I'm going to say something about X. So it's a set of all X, and then we usually use a colon or a line here. Line or a colon. So A is a set of all X such that X is greater than 2. And let's pretend that we're in the context of integers. Then this would be the set containing 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc. Do you understand what I'm saying there?
Mm-hmm.
So it's a set of all X, maybe here's how we say it. Let's be real precise. Set of all X where, or such that X is an integer. Do you remember that notation? X is in this set. X is an integer. This was shorthand for all the integers. You remember what integers are?
Yeah.
Okay. What are the integers?
They're like counting numbers.
What are the
The
counting
whole
numbers?
numbers.
The whole numbers. The integers is all the whole numbers, positive and negative. Right?
Yeah.
So I can say, this is a set of X, where X is an integer, and X is greater than 2. Does that make sense? That's more precise. Now notice what this set is equal to. This set is equal to this set. Is 2 in the set?
No.
No, but it's equal to the set 3, 4, 5, 6. How many elements are in here?
Forever.
Forever elements are in here? It's a very precise number. There's infinite elements in there, right? Correct? So that's one of the nice things about set builder notation. We can define a set that's infinite in size really short. Defining it this way, how do I write out all the integers greater than 2? I can't. So we have set builder notation to help us talk about infinite sets. Let's define these two sets in terms of set builder notation. So let's pretend right now you didn't know what A is and you didn't know what B is. And let's talk about what A union B is and what A intersect B is. So A union B, that's the set of all X such that, or where, X is in A or X is in B. If X is in A or X is in B, then X is in the union of those two sets. Does that make sense?
Yeah.
Similarly, we can define this one. What's this one?
X is in A and X is in B.
And, perfect. X is in A and X is in B. And just to be very clear, when we use or here, we mean the logical or. Would you understand what I said if I said exclusive or? Does that mean anything to you? So sometimes in the English language, we use or two different ways. Sometimes we mean the logical or. What's the logical or? The logical or is this is true, or this is true, or they're both true, right? The exclusive or is this is true and this one's false, or this one's true and this one's false. So when we say or in the English language, It can mean either of those two ways, and you typically infer from context what the person's saying. But chances are you've used or that way, both those ways. So we mean the logical or here. This is true, or this is true, or they're both true. Does that make sense? Okay.
I was just thinking or is way more inclusive than and.
Yeah.
So what's more inclusive, or and?
It has more truths on the truth table.
Yeah, that's funny.
All right. So that's set builder notation, and those are sets. You feel vaguely comfortable with sets? A little bit comfortable with sets? Okay. So now let's go over what a loci is. Well, a locus. Loci is a plural for locus. Maybe he doesn't introduce it that early.
In this chapter, we use the term locus.
Okay. A locus of points is a set of points meeting some criterion or satisfying some condition. Okay? So we've talked about sets in general. Now a locus is a special set. It's a set where everything inside there is points. No numbers, no letters, no SpongeBob, no Patrick, just points. Meeting some condition. Okay? So it's always going to be the set of points such that some condition about the points. That's what a locus is going to be. Does that make sense? It's just a special kind of set. So we can still take unions of loci. We can take intersections of loci. Loci is a plural, locus is a singular. So if I talk about the locus of points, I'm talking about one set. Does that make sense? Okay. So definition 13.1. Let's write it out to make sure we understand it. So definition 13.1. A locus of points is the set of all points comma, and only those points comma, which satisfy some condition. Which satisfy some condition. Good? So let's talk about some examples real quick to make sure we understand what exactly this definition is talking about. So if I say the locus of points at a given distance r from a given point, what is that? If I say the locus of points that are a particular distance or a given distance, let's say that again.
Given.
The locus of points at a given distance r from a given point. So here's a given point. Now I want to talk about the set of all points that are exactly r away from this point. What is that? So let's pretend that this distance right here is r. And let's mark out all the points that far away. That point is roughly that point, that point, that point, that point, that point. And if we get all the points, then we get a circle, right? Mm-hmm. So there's another definition of a circle in terms of a set of points. And we always thought about a set of points when we thought about circle. At least I did. I don't know if you did. But there we go. So let's look at another one. The locus of points at a given distance d from a line. So let's say that I've got some line here. And d is this distance. Here's d. What are all the points distance d from this line?
Rectangle? No. It's like an oval. What are you
Well,
trying to
not this line segment, this line.
Oh. parallel lines.
Two parallel lines, right? We have one up here, all dotted even though it shouldn't be dotted, and one down here. These two lines, parallel to this line, are the set of all points, distance d, from this line, right?
Mm-hmm.
Good. So
would D be the condition?
this is the set of all points, distance d, from this line. This is the set of all x such that the distance from x to L, our line L, if we call this line L, is equal to d. Maybe something like that, where this is a distance function. Right? Now, we don't have this exactly defined for a line, but you understand the idea, I think. Alright, let's look at another one. What if I say that I have these two lines, how exactly does he word it? Let's see. The locus of points. So now I want the set of all points equal distance from both those lines. What does that give me? What's a point that's the same far from both those lines?
The center line.
Perfect. That's a line that is exactly in the middle of those two lines. Right? Getting comfortable with this word locus? Set of all points satisfying some condition. Alright. So now let's use the idea of a locus in our proofs. So how you're typically going to use locus in proofs, well, not typically. A common example is if I want to say that some set of points satisfies two conditions, the way I do that is I say, let's look at the set of points that satisfies one condition, let's look at the set of points that satisfies another condition, and show that those two sets are equal. Does that make sense? So if I want to say A satisfies condition C1 and C2. If I want to prove that that's the case, then what I do is I say, let B equal the set that satisfies C1, let C equal the set that satisfies C2, and then prove that B and C are the same set. Does that make sense? But we'll see it in action real quick here with the theorem. Maybe that'll make more sense. So let's see what the theorem wants us to do. The locus of points P, equidistant from two given points A and B, is a set of points on the perpendicular bisector of segment AB. So let's get a picture for that. So this was Theorem 13.1. Before we write it out in words, let's see the picture and then we'll write it out in words. We're saying if I have some perpendicular bisector between point A and B, so we've got, there's midpoint C, the perpendicular bisector where these are right angles, and then obviously the perpendicular bisector goes down. So I'm saying take all the points that are on the perpendicular bisector of A and B, and then take all the points P that are equal distance from A and B, and those two sets are the same set. Does that make sense what I'm saying? So every point that's on the perpendicular bisector is equal distance from A and B, and every point that's equidistant from A and B is also on the perpendicular bisector. Does that make sense?
No.
Here's what I'm saying. Pick a point on the perpendicular bisector. What's the perpendicular bisector? it's the 90-degree line that goes right through the midpoint. So I'm saying if you pick a point on the perpendicular bisector, then it's going to be the same far away from A as it is from B.
Oh, yeah.
Now, pick a point that's the same far away from A as it is from B.
Oh, that's what you mean.
Then it's on the perpendicular bisector. That's what we're going to prove. And the way that we're going to do it is we're going to take the set of points that's one, take the set of points that's the other, and show that they're
the same.
subsets of each other. Right? If A is a subset of B and B is a subset of A, then the two sets are equal. That's our overall strategy. So let's write out the language exactly to help us once again get familiar with what this is saying, and then we'll go over the proof. So let's see what it says. The locus of points P equidistant from two given points and we're going to call them A and B, is a set of points on the perpendicular bisector is the set of points on the perpendicular bisector of the segment AB. Okay? So, you understand what the theorem's stating? Okay, so let's start it. Which way do we want to prove first? Do we want to prove that a point on the perpendicular bisector is equidistant, or that a point that's equidistant is on the perpendicular bisector? Maybe I'll be really explicit here and define my two sets and show that they're subsets of each other. So maybe we'll get crazy with it. Let's see, what am I going to use for my sets so that you don't get confused with points? Let S1 be the set of all points equidistant from A and B, comma, and let S2 be the perpendicular line through, or perpendicular line, or perpendicular bisector of segment AB. Alright, so you understand what set of points S1 is? What's S1?
All the points that are equal distance from A and B.
Perfect, and what's S2?
All the points that lie on the perpendicular bisector.
Of AB. Perfect. Okay, so to prove this theorem, I need to prove that S1 and S2 are really the same set, right? To do that, I need to prove that S1 is a subset of S2 and S2 is a subset of S1. How do I prove that S1 is a subset of S2?
You look at the point P.
I prove that if I take a point out of S1, that point is also in S2, right? If that's true for every point, then S1 is a subset of S2. So I'm going to pick some random point out of S1 and show that it's also in S2. So any random point you pick out of S1 is also in S2. Therefore, S1 is a subset of S2. You follow the logic there? So let's do it. 2. Let P be some point in S1. right? If P is in S1, then what do we know?
It's equal distance from.
We know
A
that
and B.
this distance, maybe I'll switch to red to draw my picture. We know that this distance and this distance are the same, right?
Mm-hmm.
Now there's two possibilities here. Either P is C or it's not, right?
Mm-hmm.
P and C could be the same point. There's no reason that they can't be. Do you understand what I'm saying? I picked some random point that's equidistant from A and B. Is C equidistant from A and B?
Yeah.
Then it's possible that P and C are the same point. Now, if P and C are the same point, maybe I'll deal with this technicality after the proof. Forget that for a second, and then I'll come back and mention it. Let's just pretend right now that P is not C, so we have a triangle. And then I'll come back to where that's from. So, we have P is equidistant from A and B, right? So this side's the same long as that side, right?
Mm-hmm.
So this triangle is a...
Isosceles.
And what do we get for free when we got an isosceles triangle? What do we know right out the door? Do you understand what we're trying to show now? We're trying to show that... We don't know that's a right angle. We're now trying to show that this angle and this angle are right angles. That's what we're trying to show.
But don't
Well, we have two angles.
And we know that that angle and that angle are right angles if those two angles are congruent. What's the definition of right angles?
two congruent angles.
No.
Equal 180.
Yes. Congruent supplementary angles. If I have congruent supplementary angles, I have right angles. Right? So I need to prove that this is congruent to this because these two angles are supplementary. You see that they're supplementary? Because if this is a right angle and this is a right angle, then P is on the perpendicular bisector.
Okay.
So that would mean that P is also in S2, which is what we're trying to show. Okay? So that's what we're trying to show, is that those two angles are right angles. How can we get there? C's the midpoint of that line. So we also know that this distance is the same as this distance.
You know the midline.
And we know the midline. So we didn't even need what I was hinting at. I was hinting at this angle and this angle are the same.
Side.
But we can actually use side, side, side to say that those two triangles are congruent. Therefore, that and that are right angles. Right? So let's put this into English now. Let P in S1, comma, and did we say anything about what C is?
No.
And let C be the midpoint of AB. Alright, now, so you understand the proof idea, right?
Mm-hmm.
Now let's handle the one weird case. What if P happened to be the point C? Is C on the perpendicular bisector of A and B?
Yeah.
How do you know that?
I don't know.
Yes! The midpoint is on the perpendicular bisector. What's the perpendicular bisector?
Well, I
It's
have
the
bisector.
90-degree line that goes through the midpoint. That's what it is. So if P is C, we're already done. Obviously C is on the perpendicular bisector. Right? So we don't really care about that case. All we care about is the case where P is not on C. Then we need to show that it's still on the perpendicular bisector. Good? Alright. So let P and let C be the midpoint of AB. 3. Observe that if P is equal to C, comma, then P is in S2. Right? S2 is a set of all points that are on the perpendicular bisector. C is definitely on the perpendicular bisector. So if P happens to equal C, then we already know that P is in S2. Good?
Mm-hmm.
Now, if P is not equal to C, then we still need to show it's in S2. 4. If P is not equal to C, comma, then triangle ABP is an isosceles. I can't remember how to spell isosceles.
ISO.
There's no way it's SC, is there?
Isosceles.
in it.
I can't believe I
I
just
think
spaced that.
it's
I've probably written this word like
CLS.
50 times this semester. Isosceles
It definitely has a C in it.
is an isosceles triangle. There we go, isosceles triangle. There's a picture for it. Boom. Right? If ABP, or if P is not equal to C, then ABP is an isosceles triangle. Right? 5. Since AP is congruent to BP, AC is congruent to BC, and CP is congruent to CP, then triangle APC is congruent to triangle BPC, comma, and angle ACP and angle BCP are right angles. You follow the logic there? Since that side's congruent to that side, that side's congruent to that side, and that side's congruent to itself, these two triangles are congruent. And therefore, this angle and this angle are right angles. Right? Therefore, P is on the perpendicular bisector. Right? Therefore, P is on the perpendicular bisector, or in other words, P is one of the points in the set of all points that make up the perpendicular bisector. You see that? So let's go over creative thinking one more time. So we had set S1 and S2. We took a random point out of there, and we showed it's also in there. So any random point you pick out of here, we showed you how to show it's also in here. So any point you pick out of here is also in here. So we just showed that S1 is a subset of S2. We said, look, grab any random point out of S1. Now, it's either going to be point C or not point C. If it's point C, then it's also in S2. And if it's not C, then here's how you show it's still in the perpendicular bisector, and so it's also in S2. So we showed every point in here is in here. You follow the logic there? Now, just because we showed that every point equidistant from these 2 points is on the perpendicular bisector, that does not mean that every point that's on the perpendicular bisector is equidistant from those 2 points. Does that make sense what I just said? For example, I could prove that every even number is an integer. That does not mean every integer is an even number. I proved every point that's equidistant from both these points is on the perpendicular bisector. That does not mean every point that's on the perpendicular bisector is equidistant from those 2 points. Every even is an integer, not every integer is even. We showed that this is a subset of this. We have not shown that this is a subset of this. Now, it turns out this is a subset of this, but it's important that you understand that we have not shown that yet. Am I losing you in all this set stuff? Putting you to sleep.
No, I'm just really tired.
You're just really tired? Like you're
I've
gonna
been
go to
tired
sleep?
all day. It's not
Why?
because of this class. I don't know.
Quit it! Do you need to do some laps? You can wait. Wake up! Does that help? No? I'll have Mark carry at some point in the class. So now be ready. Okay. So now we need to show the next way. We need to show that S2 is a subset of S1. Right?
Yeah.
And so let's change what we know over here. Erase all the red. Yeah. So this time, we're going to pick a random point P that's on the perpendicular bisector. So we know that this and this are right angles. We need to show that P is equidistant from A and B. You see what I'm saying?
Mm-hmm.
Now, what if P and C are the same point? Obviously, C is equidistant from A and B. It's the midpoint, right? So we're going to assume that P isn't C. Try and challenge ourselves here and show that it's still true. It's true for every point on the perpendicular bisector, not just C. Good? So, if we know that P is on the perpendicular bisector, once again, we've got our two triangles, right? And now we're trying to show that that distance is the same as that distance. Right? How are we going to do that? What else do we know?
Don't give him stats.
You know that those AC and BC are the same.
Right, we still know that's congruent to that. Okay.
Same with middle line is congruent to itself.
This
and
middle line is
side
congruent to itself.
Side.
So by side angle side, these two triangles are congruent. So this distance is the same long as that distance.
Just give him stats.
All right. Due to lack of space, I'm not going to bother writing out the second part of this, but let's make sure you understand it. Do you understand how you would write that out? You'd start by picking some random point in S2. If that random point is C, obviously it's also in S1. If that random point's not C, then here's how you prove it's also in S1. So every point in S2 is also in S1. Every point on the perpendicular bisector is also equidistant from A and B. So now we show that those two sets are the same. If I say the set of points equidistant from A and B, that's the exact same thing as saying the set of points on the perpendicular bisector of segment AB. Those two statements are saying the exact same thing. Do you see that? They're talking about the exact same set. Good? All right. That's Theorem 13.1. Let's do another one like it. Theorem 13.2. Maybe I can erase this loci definition now, or locus definition. And it's a similar one, except for now we're going to talk about an angle bisector and points equidistant from either side of the angle. So maybe start with the picture and then we'll write it out, the verbiage first, or verbiage after. So this is Theorem 13.2. And what it's going to say is that if I have some angle, and I have the angle bisector, if I take the set of points equidistant from the sides of the angle, that's the exact same point as the angle bisector, not including the vertice. Does that make sense?
What did you say?
Imagine the set of points that are equal distance from both sides of the angle. That's going to be this dotted line, right? Now imagine the angle bisector. That's going to be this dotted line, right? Showing those two are the same.
Yeah.
That's what I'm saying. With the exception of that point, the vertex.
So we just did that for a special case of a straight angle.
Yeah, you could think about it that way. You could think about a bisector of a segment as a special case of a straight angle where the midpoint of the segment is considered the vertex of the angle. Okay.
Except in that one, the vertex is part of the set of points bisector. No, it's not. Never mind.
Okay. So, someone want to read me the exact verbiage so I don't have to keep looking back and forth?
The locus of points interior to an angle and equidistant from the sides of the angle.
Locus, capital. The locus of points
Interior to the angle, to an angle. And equidistant from the sides of the angle. Is the set of points on the bisector of the angle. Excluding the vertex.
except the vertex. Something like that. And then I'll label my picture the same way that they do. So in case you're filling in the book, O, A, B, P. So they call this O, they pick some random point A, some random point B, and then we've got P. And we're obviously going to be talking about that. My picture's bad, but the proof should make sense either way. So, which way do we want to prove this first? Maybe I ought to make a point. So when we did the last proof, we made it very clear what set S1 was, what set S2 was, and we showed that S1 is a subset of S2 and S2 is a subset of S1. Right? In general, you kind of are doing that stuff behind the scenes. What you do is you say, pick a point that happens to meet one condition and show it meets the other condition. And then pick a point that meets the other condition and show that it also meets the one condition. You see what I'm saying? We have two conditions that we're always talking about. In the last proof, those were the perpendicular bisector and the set of points equidistant from the 2 points, right? Those were the two conditions. We showed all the points that meet the one condition also meet the other condition. And then we showed vice versa. Right? In general, or not in general, but in practice, when you're writing out these proofs, you don't usually take the time to specify this set showing this set's a subset of one and this is a subset of the other. You say pick some point that meets one condition and show that it also meets the other condition. And then vice versa. So this time I'm not going to write out all the sets and then I'll talk about how we're actually using those sets. It'll be more like how I'm sure the author proves it. So we'll start out with which one. Should we pick a point that's equidistant or should we pick a point that's on the bisector?
Equidistant.
Alright. So let P be a point interior to the angle and equidistant from its sides. Okay. So let's go over the proof sketch and then we'll write it out. So I know that this point is equidistant from from the sides, right? What does that mean? That means that if I drop a perpendicular down to this line and a perpendicular down to this line, this side is the same long as this side. That's what it means to be equidistant from those two lines. Okay? Does that make sense? Alright, so there's what we know. Now, what are we trying to prove? We're trying to prove that P is on the angle bisector. Or in other words, we're trying to show that this angle is congruent to this angle. You know what the angle bisector is? It's the line that splits the angle, or the ray that splits the angle into two congruent angles. So, we can show that angle is congruent to that angle, which we get if we can show that this triangle is congruent to this triangle, right? How can we show that those two triangles are congruent?
Can you look at O and B and O and A?
O and B and O and A, and what about them?
They're the same length.
How do you know that?
It's gotta be in the definition of our distance.
No, it's not.
That's weird.
Well,
Oh,
first
no,
off,
I see why it's
one obvious thing, that line's congruent to itself. And so those triangles are, what kind of triangles? Left?
They're right.
Ah, they're right triangles. So these are right triangles, and something very cool about side lengths holds for right triangles. It's a very cool theorem, the only theorem you knew before you came into this class.
Pythagorean.
Ah! Building up the suspense, the Pythagorean Theorem. And the Pythagorean Theorem tells us that the square of that plus, or the square of that plus the square of that equals the square of that, right? So that squared minus that squared gives us a number. That squared minus that squared gives us a number. If those are the same and that's the same, then those are the same. Do you understand what I'm saying?
Yeah.
Maybe write it out one more time using, let's call this length over here A. This length over here is the same, we'll call it A. We'll call this length C. I know that, we'll call that X, and I call that Y. So I know that C squared minus A squared equals X squared. And I know that C squared minus A squared equals Y squared. Right? Substitute in Y squared for that. Y squared equals X squared. Distances are always positive, so we can ignore the negative case. So Y equals X. You follow that logic? Now, that's the logic for a theorem that we actually proved that said that if you know that the hypotenuse and a leg of a right triangle is congruent to the hypotenuse and a leg of another right triangle, then the two triangles are congruent. So we had a theorem where we proved that, but we used the logic that I just wrote out to prove it. Does that make sense? Okay. So we do know that those two things are congruent. There's a special theorem for right triangles that tells us that's congruent to that. Or this triangle is congruent to this triangle, and so that angle is congruent to that angle. Okay? That's that direction. Now what about the other direction? So I'll maybe just erase the picture and start again, rather than trying to erase all the red. So we've got some angle. We've got that. Here's O. We'll be having an A and a B. So this time, let's pick a point on the angle bisector. Right? So I pick P over here on the angle bisector. There it is. Magic P. If it's the angle bisector, what do we know?
That those two angles are congruent.
We know that this angle is congruent to this angle, right? Now what? I guess we haven't talked about A and B yet. What can we do? So let's get rid of those for a second. What can we do? We're trying to show, what are we trying to show? We're trying to show that P is the same distance from here as it is from here, right? So let's get its distance real quick. How do we get its distance? We drop a perpendicular down to the line. Drop a perpendicular down. And maybe we'll call this point up here A, where that meets. Right? Now what? Maybe pick a point over here, B, so that this distance is the same as this distance. Maybe draw that line. We don't know if that's a right angle,
Why not make it a right angle?
because I'd rather make this the same long as this rather than drop a right angle down and just know those angles are the same. But we could have. If that's more intuitive to you, then let's do that. So let's drop another angle down here. Or another line segment down here, so that's a right angle. Okay. Now what? Come on! Look, what are our congruence theorems? We can do side, side, side. We can do side, angle, side. We can do angle, side, angle.
What about angle, angle, angle?
No,
No,
this
you
gives us
know
similar triangles.
the line that bisects it.
Huh?
It's the same line. OP is the same line as PO. Or yeah.
Well, that's not fair.
We don't know that. Oh, you're saying this line's the same as itself?
Yeah.
Oh, sure. There you go. So that line's the same as itself. Yep, you know that.
Oh wait.
Oh, you're killing me. What's the sum of the angles in a triangle?
180.
180. So all the angles in this triangle add up to the same thing that all the angles in this triangle add up to, right?
Oh, so those two angles have to be the
Yeah.
same.
Oh, there you go. So this angle has to be congruent to that angle, right? And so those triangles are congruent by side, side, side. No?
Angle, side, angle.
Oh, by angle, side, angle. There we go. Angle, side, angle. Those two triangles are congruent. There we go. So yeah, you could have done it that way. Do you see how we finished the theorem? We showed that every point that's on the angle bisector is equidistant from those 2 points. And we showed that every point that's equidistant from those 2 points is on the angle bisector. So we showed that those two sets are congruent, or are the same set.
Or subsets.
One's a subset of the other, and the other is a subset of the one. Do you see how we did that?
Mm-hmm.
Does that make sense? Okay, should we write out this proof, or do you think you got it?
Got it.
You got it? So you can write it out? You can't write it out? So you don't got it?
I understand the process. I'm bad at writing it out.
There's no difference between those. If you can't write it out, you don't understand the process. You might understand big picture what to do, but you might get stuck somewhere.
No, like I skip things. Usually.
You skip things in the process.
I don't know how to explain it.
You skip steps. You assume things that you don't explicitly tell whoever's doing your proofs.
Yeah.
No, that's fine. We can follow your skips. You ready?
Sure.
Okay. Then we won't worry about it. Next theorem. Theorem 13-3. Let AB be a given segment, and then the set of all points P such that that triangle is a right triangle with AB as a hypotenuse is a circle on AB. Okay. So here's what this theorem's saying. We've got Always start with your circles when you have to do a circle in a drawing. Alright. Got our circle. That doesn't look like a circle for some reason. Laura. What'd you do? Alright. So we've got a circle with AB as its diameter. And then we can also use A and B. We can also use this line segment and we can construct any right triangle that we want. So here's P, here's a right triangle. What are we saying? We're saying if I can make a right triangle with AB as my hypotenuse, then this other point is going to be on the circle that has AB as its diameter. And conversely, if I take some point on the circle that has AB as its diameter, besides A and B, so I can make a triangle, if I take some point on the circle that has A and B as its diameter, then that point makes a right triangle. Okay? So which way do we want to start? Do we want to show that if it's a right triangle that the point's also on the circle, or do we want to show that if the point's on the circle it's a right triangle?
If the points are on the circle, then it's right triangle.
Alright, let's start with that one. So what do we know? We know that A and B is the diameter of a circle, and P some point on the circle other than A and B. We need to show that this is a right angle. Okay? How can we show that's a right angle? What's our ideas?
Use the loci and say that it's going to be the same distance all the way around. Maybe.
So you're saying, find the center of the circle here, call it O, and you're saying calculate this distance and show that this distance is the same as that distance?
Mm-hmm.
That's one way to do it. And we could do it that way using the Pythagorean Theorem if we drop down a right angle there, but there's a much simpler way I can think of using the last theorem that we did last time. I think it was the last theorem last time.
Well, could you...
The theorem that we did last time says that if I have some inscribed angle in a circle, and I tell you that this arc length is 20 degrees, how big is this angle? So if we use the center of the circle, there's O. If I tell you that this right here is a 20-degree angle, how big is this angle?
20.
It's 10 degrees.
Okay.
It's half of it.
How's it? Wait. How's it? Oh, okay. I see.
No, I was 20.
It's 10.
I was 20.
Do you remember this theorem?
Last selection.
The last theorem. You didn't watch.
Oh, it's just me and Nicole.
Our life.
Yeah, I think it was. Let's see. Theorem 1211. The measure of an inscribed angle in degrees is equal to 1/2 the degree measure of the arc it subtends. The arc it subtends is 20 degrees. Here's an inscribed angle. It's 1/2 of the arc it subtends. 10 degrees. All right. If we view APB as an angle, what is the arc it subtends? How big is this arc from A to B in degrees?
180.
180 degrees.
It's not 200.
So that's 180 degrees. And if this angle is half that, then what's this angle?
I missed that. What did you say?
So the subtended arc from A to B is 180 degrees. Our theorem tells us that if we have an angle inscribed in a circle, then that angle is 1/2 the angle subtended by this arc. So if this is 180, then what's that angle?
90.
What's 180 divided by 2?
90.
Yeah, 90. So that's a right angle.
Don't do that to me.
Okay, so that was going the one way. Do you see how the logic there? We picked a point other than the diameter. That gives us an inscribed angle. This will always be 180 degrees, so this inscribed angle is half of it, 90 degrees. Good? Alright, let's do it the other way. So now, we know that, so we have A and B, and we have a right triangle. With some point P right there. How do I know that P is going to be on the circle that has AB as its diameter?
That it has to be on the circle?
Yeah. So, how many circles circumscribe a triangle? Well, maybe get rid of the circle. Maybe this will help you see it better. So let's pretend that we start here. So I've got point A and B as a hypotenuse of some right triangle. I'm trying to prove that then this point P is on a circle that has A and B as its diameter. Right? Now, hopefully you remember this theorem. How many triangles, do you remember what it means for a circle to circumscribe a triangle? If I have some triangle, then the circle that circumscribes it is a circle that goes through all of its vertices.
Okay.
And there's one and only one circle that
Does
circumscribes a particular triangle. Okay? So, I start by making the circle that circumscribes this triangle. Alright. So there's a circle that circumscribes this triangle. But I don't know that A and B is a diameter. Right? So now, how do I prove that AB is the diameter of that circle?
You look at its angles.
What angles?
P. Angle APB.
Okay, what about it? It's a right angle. So what?
So then it's that theorem.
Yeah, so then this has to be 180 degrees. Therefore, this is half the circle. And we're done. P's easy or easy peasy?
Cool.
Good? I don't know how the book does it. That's the easiest way in my mind. I'm sure that doing it the way you were thinking about would have worked. Using the Pythagorean Theorem to prove that those distances are always the same, but that's a lot of work. And I wouldn't want to prove it that way without analytic geometry. Which we'll get to. Okay. Unions and intersections. We already went over this a little bit, but let's cover it one more time. Given two sets of points, S1 and S2, the union of the two sets is a set of all points S1 and S2. Set of all points of S1 and S2.
I thought
That's
it was
confusing
or.
to use an and there.
Yeah.
Well, read it carefully. Let's go over it one more time. Given two sets of points, S1 and S2, the union of the two sets is a set of all points of S1 and S2. So that's a set of all points in S1 or in S2. Yeah, I don't like how he used and right there. But his statement is still correct.
Too inclusive for my taste.
But it's the same definition that we said. The intersection of S1 and S2 is a set of points that are common to S1 and S2. I like our way of saying it better. I like using or in union and in intersection because they actually play very similar roles.
So
The
you're
logical
saying-
or and is very similar to the set, union, and intersection.
So if the set, so S1 has 1, 2, 3, 4, 5, and S2 has 1, 2, 3, the A union of that set could be 1, 2, 3, 4.
No. There is one and only one union of two sets. It's well defined. What does it mean to be well defined?
My point is when you say or, then it feels like when you use or, then you could have
Let's-
multiple options.
Let's set up the exact case that you're saying. A is equal to the set, what did you say? 1, 2, 3, 4, 5?
Yep.
And B is equal to the set, what did you say? 1, 2, 3?
Mm-hmm.
Alright. Now, remember how we said what union was with set builder notation. So let's think about that. So now I want the set of all x such that x is in A or x is in B. Okay? Let's build that. Let's see what's in there. Let's start with 1.
True.
Is 1 in A or in B? Is that statement true?
Yes.
Okay, so the 1's in there. Is 2 in A or in B?
True.
Yes.
Is 3 in A or in B?
Yes.
Is 4 in A or in B?
Yes.
Is 5 in A or in B?
Yes.
So the union of those two sets is always out. You can never get a different set doing union, the same way that you can't get a different number doing plus. I can't take 6 and 8 and add them together and get two different numbers. If I did, addition wouldn't be well defined. I can't take the union of two sets and get different sets, or a union wouldn't be well defined. We wouldn't be able to use it because you never know what you're going to get. Does that make sense?
Yeah, it does.
So that's why I like
Or.
the or here, the logical or there. And it should be very clear if you write it out what exact elements satisfy those conditions. Right? So if B is a subset of A, then the union of AB is always just A. The union of a set with any of its subsets is just that set again. Right? 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 Mm-hmm. In the classroom, jeez. Okay. Let's do another proof. Or another theorem. So that was the definition. You understand the definitions. So Theorem 13-4. The bisectors of the angles of a triangle intersect at one point, we call it the incenter, which is equidistant from the three sides. So let's make sure we understand what this is saying and understand how this is using the intersection. So we're talking about Theorem 13-4. Did we skip 3? Did we skip 3? Or did we just talk about it and never write it? We just talked about it? Yeah, we're on 13-4. So Theorem 13-4, what's it talking about? It's saying if you have some triangle, take its, where'd I put my right marker? Oh, under the eraser. Take its angle bisectors, it's saying all those angle bisectors are going to intersect at one and only one point. Okay? Do you understand?
Yes.
You busy texting?
Yes, but yes. You're gonna look at all those three lines as a set, and then you're just.
Well, I can take this line and this line, look at their intersection, and show that that's also the same as the intersection of this line and this line. Something like that, right? Because we already know two lines intersect at most 2 points, right?
At most.
Yeah. Lines intersected at most 2 points.
What?
What? They intersect at 0 points or
oh.
1 point or 2 points, right?
Okay.
No! Lines intersect at one
1
point or
point.
no point, or they're the same line.
I was thinking that line has 2 points that it intersected at.
So pay attention to what I'm saying so the logic makes sense. We're going to take the intersection of this angle bisector and this angle bisector, which gives us 2 points.
No, it doesn't.
Oh, which gives us 1 point. And then we're going to take the intersection of this angle bisector and this angle bisector, which gives us 1 point, and show that they're the same point. So then all three of them intersect at the same point. That's what we're trying to show. Okay? So, let's read the theorem one more time carefully. The bisector of angles of a triangle intersects in one point called the incenter, which is equidistant from the three sides. Oh, which is also equidistant. And I won't bother drawing it past that, so that we kind of don't make a mess. What should we call it? Point O, I guess. And we're showing that this point, the distance from this point to this side is the same as the distance from this point to this side is the same as the distance from this point to this side. In other words, that distance, and that distance are all the same. Good?
I thought we were showing those three lines are the same.
Read it one more time. The bisectors of the angles of a triangle intersect at one point, which is equidistant from the three sides.
Okay.
You should skew one of your angles.
Okay. So, let's have some points to talk about. This is green. This isn't stuff changing. Let's give our triangle some points. So that's A, that's B, and that's C. Okay? So let's look at just two of them for a second. So we'll look at the angle bisector from A, which continues like that, and the angle bisector from B, which continues like that. Okay, first off, we showed all the points on an angle bisector are what? What was the last theorem that we did?
Equidistance from A and B.
Equidistance from these two lines. Angle bisector.
Oh.
Right? So we know that the distance from this point to this line is the same as the distance, because, maybe get rid of these so I can do this better. Because this point is on this angle bisector, the distance from this point to here is the same as the distance from this point to here, making those right angles, right?
Yep.
That's the same as that, okay? Now, looking at this angle, this point is on this angle bisector, which means that its distance from here is the same as its distance from here.
Yep.
Right? You follow me so far? Maybe let's recover one more time. Start from the very beginning. So I've got some triangle ABC. I pick an angle bisector, and I pick an angle bisector. How do I know that those intersect at a point?
Well, they have to.
They're not parallel.
They're not parallel.
Yeah, they're not parallel, so those two lines intersect at one and only 1 point. Call it O. That's how we find out. Now, I know that since O is on A's angle bisector, that the distance from here to here and the distance from here to here are the same.
Your lines are really throwing me off.
Are they? Alright.
Thanks.
Let's draw some triangle. Let's get out my protractor. 65.
What the heck?
So 65, so we're looking at 32 and then some, something like that.
I was talking about bisect.
Here's where red comes in. Any guesses on this angle?
73.
82.
Holy cow. That is 70 right on the money.
Ah.
35.
Oh, pay up.
Crazy coincidences.
So you owe me 10, Hunter owes me 20.
What?
For losing one.
The next one's gonna be like 57.
We don't measure the next one.
But I'm just saying.
Sorry, what's it gonna be?
Because we already know that next one goes through that point, so I can just give it.
Yeah,
Okay.
know it, no,
Anyways.
I do.
Yeah.
There is O, which is the intersection of this angle bisector and this angle bisector, right? Now how am I going to draw a perpendicular?
You have to draw that other line.
So I'm going to erase this part of it, or maybe we'll make, yeah, we'll just erase that part of it. We don't need that, and we don't need that.
Draw a nice speed square.
You got it?
Try.
I'll just use this to make a 90-degree angle. So now we take the 90-degree off of this to get the distance to the line over here. Oh, crap, wrong 90. I need the 90 off of here, which is that line. Which means I'm going to have to go a little bit of eyeball on. I don't want to actually make the construction.
Wait.
Pretty close. Maybe I'll just do it like this. Line that up. Like that. There's that one. Now, we'll line up. That one.
Are you doing all four? Right off the bat.
Okay.
Why did you pick those two?
Ah! Why didn't you tell me I was doing it wrong?
I was asking if you're doing all four.
Oh, crap. This one. Okay, we don't care about this one. Well, it's fine. Okay. So,
All four. Two of them are the same.
here was A, here was B, here was C. Okay. So I have my bisector of A and my bisector of B intersecting at a point. Right? I know that the distance O is from this line and the distance O is from this line are the same. So that is congruent to that. Good? Now, O is on the perpendicular bisector of B. Right? So I know that that distance and that distance are the same.
Mm-hmm.
Okay?
Yep.
So O is equidistant from all three sides. Furthermore, since O is equidistant from that side and that side, O is on the angle bisector of C. So O is the intersection of all three angle bisectors. And it's also equidistant from all three sides. You follow that logic? What's the logic?
So you basically prove that, you show that those two intersect at point O,
Right?
B and A. And then you do the 90-degree angles from them,
Right? The distance is 10.
yeah, which are all equal. Then
Why is that equal to that?
because of the last theorem we did with
Which
the angle.
what? Where it says
Proving
what?
that the sides of the angle are equidistant from perpendicular bisector.
From the bisector.
In
Not
point.
perpendicular, just the
Sorry.
bisector.
I didn't mean to say that.
So you take your angle bisector, every point on the angle bisector, including O, is equidistant from both sides of the angle. Therefore, O is equidistant from both sides of the angle. So that gives us that congruent to that. Same thing holds. O is on the perpendicular, or on the angular bisector of B, and therefore it's equidistant from both the sides of the angle of B. And then since O is the same distance from this side of angle C and this side from angle C, then O has to be on the angle bisector of C as well. Right? Got it? That's that theorem. Picture clear enough for you? Or is it still a little off? All right. That's theorem 13.4. Do you guys want to write that one out, or do you think you're good?
I think I'm good.
Think you're good? All right. Move on to theorem
What do
13.5.
you think you're good at?
The bisectors of the angle of a triangle. No, that's 13.4. 13.5. The perpendicular bisectors of the sides of a triangle intersect in one point called the circumcenter, which is equidistant from the three vertices. Oh, by the way, why do we call this in-center?
Because it's not outside.
Because all the sets are, or it's the union between all the sets.
It's the center of the inscribed circle. So if I draw the circle that I could fit inside of there, the biggest circle I could fit inside of there, its center is right there. And it's a circle that goes through this point, and this point. It's tangent at those points. That's the inscribed circle, and its center is the in-center. Now we're going to do a similar thing, and we're going to call the point the circumcenter, because it's going to turn out to be the center of the circle that circumscribes the triangle. Does that make sense? Okay. So let's do that one. So this time we're saying, if we have some triangle, we take all its perpendicular bisectors, wherever they intersect. Will be a lot rougher this time, but still try and get them somewhat good. So we take this thing, we take this thing, then we take this thing, because that's the center of that side for real. So let's go over what these points were. We're saying, take the perpendicular bisector of this side, the perpendicular bisector of this side, and the perpendicular bisector of this side. And they're all going to intersect at the same point there. And that point is equidistant from here, and from here. Does that make sense? Very similar to the last one, right? So let's start with two of them, like we did last time, and work our way up to there. Get rid of that, get rid of that. This doesn't use that last theorem, does it? Let's see what we know. So I take two perpendicular bisectors, which meet at a point. Right? And I need to show that that point is equidistant from A, B, and C. How do I do that? Maybe call the point that they meet at O. We know that these are right angles, right? Furthermore, I know that that's the same long as that, and that is the same long as that. Trying to show that O is the same far from A as it is from B as it is from C.
Oh, you look at the theorem that says if there's a point on the perpendicular line between A and B, then it is equidistant.
Right. We already proved a theorem that said the set of points equidistant from 2 points is the exact same thing as their perpendicular bisector. So I know since O is on the perpendicular bisector of AC, then I know that this distance and this distance are the same. Right? Furthermore, I know that O is on the perpendicular bisector of B and A. Therefore, this distance and this distance are the same.
Mm-hmm.
Right?
Yep.
Now, finally, I know that since O is equidistant from B as it is from C, that O is on the perpendicular bisector of BC. So the perpendicular bisector of BC also goes through O. So all three perpendicular bisectors intersect at one point. Just follow that logic? Think you understand it? Very similar to the last one?
Mm-hmm.
And then the reason it's called the circumcenter is because if you were to draw the circle that circumscribes this triangle, that would be its center. Because notice that's the radius, that's the radius, that's the radius. This point, those are the radiuses. Right?
Mm-hmm.
Okay. So that's that theorem. More like this. The medians of a triangle intersect at one point, called the centroid, which is 2/3 of the distance from each vertex to the midpoint of the opposite side. All right, let's go through that. So draw some triangle. A, B, C. Now, a median line is a line that bisects this side and goes to the goes to a vertex. So here's a median. Well, let's do it from A and B like we were doing before. So take the midpoint of this side, which is somewhere like right here, right? This is a median. Does that make sense? It's not necessarily an angle bisector. Those two angles aren't necessarily congruent. This isn't necessarily a perpendicular bisector. Those two angles might not be right angles. All we know is that that is congruent to that. That's what a median is. Does it make sense what a median is? Do you know what the median is?
About the definition.
It's the line that goes from a vertex and bisects the opposite side. Does that make sense? So that's what a median is. So now our theorem is saying, take the intersection of two medians. Maybe we'll do red like we did this week. So here's one median. And then here's another median. There's their intersection. We're saying all three medians intersect at one point, and furthermore, this distance is 2/3 this distance. Or this distance is twice as big as this distance, or this distance is 1/3 this distance, or this distance is half this distance. See how those are all saying the same thing? Whichever way makes it clear in your head. If this distance is x, this is 2/3 x, this is 1/3 x. Clear? If this distance is y, this distance is 2/3 y, this distance is 1/3 y. Good? Alright, so that's what we need to prove. So I need to prove, the way I'm going to prove it is I'm going to prove that this distance is twice as big as this distance, or this distance is half this distance. Similarly, I'm going to prove that this distance is half this distance. You see how that shows that this is 2/3 of all this? If I say x is equal to 2/3 x plus 1/3 x, this piece is twice as big as this piece. Here's x, here's 2/3 x, here's 1/3 x. The way I'm going to show that this is 1/3 is show that this is half of this.
Oh. Yep.
Does that make sense? That's the logic I'm going to use. Let's see. So I know that this is the same long as this, and this is the same long as this, right? Because those are median lines. Remember, a median line is a line that goes from a vertex that bisects the opposite side. You see how I know those distances are the same? Okay, so that means that when I draw this line, then what? What do we know about that line?
It's the same as itself.
That line's the same as itself, sure. But what else do we know about that line?
James, don't answer it, it's a trap.
That is a midpoint of this side. That is a midpoint of this side. Maybe another way to say it, I'll call this point right here A prime, and I'll call this point right here B prime. Maybe look at this triangle, A prime, B prime, C, and A, B, C. What do you think about those two triangles?
Makes a trapezoid.
What? Oh. Makes a trapezoid, sure! Makes a trapezoid. What's the one special thing about a trapezoid? It has two sides that are
Parallel.
parallel! We know that this side is parallel to this side. Right? If that's the way you see it easier, the way I was going for is we knew that this triangle was similar to this triangle, but yeah, that side's parallel. So if we know that this side is parallel to this side, then by alternate interior angles, I know that this is congruent to this, and that this is congruent to this. Oops, pardon. This, right? let's draw that over here. One case over here is like that. These two lines are parallel, and I have some traversal. Then that angle is congruent to that angle, right? That's the logic I'm using. Here's two parallel lines. Here's one that goes through both of them. That angle is congruent to that angle. Okay. Here's two parallel lines. Here's a line that goes through both of them. That angle is congruent to that angle, right? And then obviously, this angle is congruent to this angle. So this triangle and this triangle are similar, right?
Yeah.
Now, how big is this distance compared to this distance?
What distance did you just ask about?
How big is A prime B prime compared to AB?
It's half.
It's half of it, right?
How do you know?
We know that this triangle is similar to this triangle. And that this is half of this, and this is half of this, so this is half of this. All the proportions are equal, right? Do you remember what it means for two triangles to be similar? All their angles are congruent, and the proportions of their sides are equal. Does that make sense what I'm saying? In other words, this distance over this distance is equal to this distance over this distance is equal to this distance over this distance. Well, this over this is 2. That's twice as big as that. So that's twice as big as that. So this is 1/2 this. Now this triangle is similar to this triangle. So if this is half of this, then this is half of this, and this is half of this. Do you see that? That's how we're proving that. So that point is two-thirds of this distance. Right? And then, if we were to draw the midpoint over here, we could do the same thing to say that this point is 2/3 of this distance. Right? Do you see how you would just do the exact same argument again? And so, the median here also goes through that point.
And that's what you're looking for?
We were showing that the median, that point, we were showing all three medians intersect at one point.
One point.
And the way that we showed that is we showed that it's always 2/3, 2/3, 2/3 away. There's only one point that's always 2/3, 2/3, 2/3. The median is always 2/3, 2/3, 2/3. These two satisfy it, therefore this last one satisfies it. It's just like we did in the other two cases. Except for in those cases we were talking about equidistance from a side and equidistance from the vertices. We said, pick two of them. They're both equidistant from the vertices. Therefore they're equidistant from the last vertice. Therefore the other one also goes through it.
Yeah.
Right? Same exact thinking there. I'm just afraid to keep adding to the picture because I think I'll confuse you. If you can get to here, you can finish the proof pretty easy, right? If you show that that's 2/3 that, and that's 2/3 that, then you could also start with this midpoint and show the same thing. Do you understand what I'm saying? Right? You could take that midpoint, you could draw the line that goes through this, and show that it also goes through there. But that's not as much the important part as understanding up to here.
You get it?
Yeah, it's just confusing for you to think about.
So the important part is, do you see how this is 2/3 of,
Except
or
for think about the picture.
this is twice as big as this?
So you need you to start.
Restart.
No, I don't.
Start and restart, we're in above.
Go through the proportionalities. She doesn't see why it is, right?
What are you talking about?
She's gonna
Okay.
ask that the chapter's on.
No, I understand.
Let's write out big picture what we went over first. We went over the fact that, first that A prime, B prime was parallel to AB. That's a way, way old theorem that we did way back there, where since they both bisect, since it bisects two sides of the triangle, it's parallel to this. And that's an old theorem. So we knew that that was parallel to this. We also knew, because of that, that triangle ABC was similar to triangle A prime B prime C. Right?
Not because of, like,
It follows from the same thing. We proved this first, and then we showed that when this happens in a triangle, this is true. And it doesn't have to necessarily bisect it, it just has to break both the sides into the same proportion. But bisecting was a simple case that we did. So we did this theorem first, and then with the help of this theorem, we were able to prove this theorem. But those are still two theorems that we did in the past. And then that gave us that A prime B prime is equal to 1/2 AB. Right? So you're good with all that. Then the next thing that we need to do is say this angle is congruent to this angle, and this angle is congruent to this angle, which is true by alternate interior angles. So then we show that angle BAO is congruent to angle A prime B prime O, and angle BAO is congruent to angle, oops, did I just say one twice? Not BAO, ABO. ABO is congruent to B prime A prime O by alternate interior angles. And then obviously this angle is congruent to this angle, but we don't even need to write that out. We just need to know that two angles in two triangles are congruent to know that the two triangles are similar. Because if two angles are congruent, the third angle is also congruent, right? If I know that that's congruent to that and that's congruent to that, then this has to be congruent to this. And we also know it is by vertical angles, but we don't need to say that. We know that two triangles are similar if they have two congruent angles. Right?
if they have two congruent angles, how many congruent angles do they have?
But they also have, and one more, 3. If two triangles have two congruent angles, then they have 3 congruent angles, and they're similar, right? You get that for free,
Yeah.
because the sum of the angles in every triangle is the same, right? And if I know that x plus y plus z equals x plus y plus a, I know z equals a. That's what we're saying. If the sum of the 3 angles is the same, and 2 of the angles are the same, then the last angles are also the same. Good? So, because that's congruent to that and that's congruent to that, then we had this triangle congruent to this triangle. Or not congruent, similar. So then we had triangle ABO is similar to triangle B prime A prime O. And so we know that AB over B prime A prime is equal to BO over A prime O is equal to, what side am I missing? AO? AO over B prime O. Length, 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 length. The proportion of their sides are always the same. So pick any 2 letters here, take the corresponding 2 letters there, that ratio is the same for all 3 sides, right? That's what it means for them to be similar. Their angles are congruent and this proportionality holds. But we already know that AB over A prime B prime is, what's that divided by that?
1/2. Or 1/3.
2/3.
this divided by this is
I'm not seeing it.
holy cow. If y equals 1/2 x, and which way were we doing it? We were saying x divided by y equals what?
Y over X.
Get x and y in the equation like this, and what do you have on the other side?
1/2.
What is it, Laura?
2.
2! Multiply both sides by 2, divide both sides by y. X over y equals 2. Or AB over B prime A prime equals 2. So that is 2, so that is 2, which is what we were trying to show. We're trying to show that's twice as big as that, or that's twice as big as that.
I see it.
You see it? You better see it. Good? Does it all make sense? What part doesn't? What? The whole thing? Well, I'm not doing it again, so tough. Alright. And then the altitudes intersect at one point. I'll let you guys read through the proof of that one. Because it's going to be similar thinking again. Huh?
As bad as the author.
No, the author's a lot worse. He doesn't even finish proving any of these.
I know, I love proof.
So maybe you can't just look at the author's proof. But all the altitudes of a triangle also intersect at one point. What are the altitudes? If I have some triangle, the altitude is add a vertice, drop a perpendicular. So that's right angle, and that's right angle. This is an altitude. And so all the altitudes intersect at one point.
What's
It's called the
special
orthocenter.
property of that? The orthocenter.
Jeez, we've already gone 2 hours. Oh. There isn't a special property of that. Oh, because you construct a bigger triangle, in which case they become just the angular bisectors.
Wait, if you construct a bigger triangle,
You just extend the smallest side of the line.
angular bisectors?
No.
No, not the angle bisectors.
The mean.
Yeah, does it become the centroid of a larger triangle?
Yes. So here's the idea of the proof on that one. We'll just go over it. So, hopefully, I'll have to draw too big. A, B, C. So those are the altitudes on A, B, C, right?
Oh.
So what we do is through A, I construct a line parallel to this line, but twice as long. So that A is the bisector of that segment. See what I'm saying?
Yep.
So I come over here, geez, it's gonna be a really big triangle, but
Wait.
now that's a perpendicular bisector of this side,
Which you're doing it parallel to BC.
parallel to this. Okay? And then, through this, I construct a line parallel to this, twice that distance. Now, since I'm not doing this right, it's not really going to work. My picture's going to be a mess. Because that should be not working out right. And then finally, same thing here. And so,
Which one of those is?
what used to be what are the altitudes of the triangle inside of here are now the perpendicular bisectors of this big triangle. And we already know all the perpendicular bisectors intersect at one point. See, this line is a perpendicular bisector for this side of this big triangle. This line is a perpendicular bisector for this side of this triangle. I know that this is a right angle here and this is a right angle here because they work here and I made this parallel to this. Similarly, this side, since this line's parallel to this line, I also know that these are right angles.
So you're trying to show those are the same point?
Well, I'm saying for this big triangle, we already showed that perpendicular bisectors intersect at one point.
Okay.
And the perpendicular bisectors of the big triangle are the altitudes of the small triangle. And so they intersect at one point.
Oh.
That's what we do. And you have to do some argument to talk about how B is the midpoint of that, and that is the midpoint of that, and that is the midpoint of that, and that.
Wait, so that's
But that's the
circle
idea.
center of the big triangle? 'Cause it's
That is the,
perpendicular bisector.
no, that is the in,
It's in
in
here,
center?
circle.
No, it's gotta be the.
oh no, it's the circumcenter, sorry. Yeah, it's the circumcenter. Because if it's on the perpendicular bisector, it's equidistant from these 2 points. And then it's equidistant from these 2 points. If it's equidistant from all 3 of those points, that's the radius for your circumscribing circle. So that's the idea of that curve. But we won't bother with it so that we can hopefully get through solid geometry. Or space geometry. So that's the end of that chapter. The next chapter, you'll notice that the author doesn't bother proving almost any of the theorems. Maybe say it this way. We have now finished plane geometry. We're done. That's the end of plane geometry. Now the author moves into three-dimensional geometry, or space geometry, and he shows how he doesn't prove the theorems because the purpose of this textbook wasn't to teach you space geometry, it was to teach you plane geometry, and he's putting this chapter in here to familiarize you with what space geometry is like and what's out there, and what we need to add. Okay? So to go from plane geometry to space geometry, we now need more postulates. Right?
Mm-hmm.
So all the postulates we had were for planar geometry. Now we need to get some postulates to extend us to space geometry. Ooh, I'm really wondering if I want to power through this or if we want to take time with this. What do you think?
Are you trying to finish the book? Stay.
No, not today. So if we do one more class, maybe we'll skip space geometry and spend more time on that next class.
Analytic.
And skip to analytical geometry. You okay with that idea? Well, let's just power through. Let's just keep following the book. Alright, so introducing new postulates to get us to space geometry. Now, you might remember some of our plane geometry postulates going clear back to the very beginning. We have postulates like there's at least 3 points, 3 non-collinear points in a plane. 2 points define a unique line, and every line has at least 2 points on it. Those were the really basic postulates that got us started. And then we had our betweenness postulates that we introduced after that. Those were the first postulates that we went over. You remember those vaguely? So now these are going to be similar to that. We need our basic postulates to get started in 4-dimensional space. In 3-dimensional space. So how do we go from 2-dimensional space to 3-dimensional space? We need a 4th point guaranteed that isn't coplanar. So just like in 2-dimensional space, we couldn't start out with there's at least 3 points. That's not enough. Because if there's at least 3 points, they might all be on the same line, and our whole geometry might be stuck on this line. the way that we got out of one line is we said that there are at least 3 points that aren't collinear. Now we have to have a plane. It takes a plane to capture 3 points that aren't collinear, right? So our first postulate now is there's going to be at least 4 points that aren't coplanar. So in other words, there's another point right here now. I can't draw the other point on the whiteboard, otherwise those are coplanar. They're in the same plane, right? So now we're saying instead, not only are there at least 3 points in a plane that aren't collinear, but there's at least 4 points in space that aren't coplanar. That's what the first postulate is saying. Does that make sense?
Mm-hmm.
And you see how that gets us that extra dimension that we need?
Mm-hmm.
So let's read the postulate exactly. There is a set of points called space. Certain subsets of these points are called planes. There are at least 4 points that are not in any one plane. So there's at least 4 points that aren't in any one plane. Or in other words, there's at least 4 points that are not coplanar.
Mm-hmm.
Does that make sense?
Yep.
That's our first postulate. Our second postulate is similar to our line one. Our line one says that there are at least 2 points on a line. This one says that there are at least 3 points in a plane. That's the second one. You see the connection, how it's similar?
Didn't we cover this like at the very start of Euclid?
Oh, oops, I said that wrong. Yeah, this is similar to exactly how we started. But now we're talking about in 3-dimensional space instead of 2. So I lied. This one's similar to the one on a line. When we says that there's exactly one line containing 2 points. This one says that there's exactly one plane containing any 3 non-collinear points. Alright, that's where we're at. So that's the second postulate. If I have 3 non-collinear points, then there is exactly one plane that contains those 3 points. So if I pick this point, and this point, there is exactly one plane that goes through those 3 points, right? If I pick this point, the point on the edge of this, and the point on the end of James's nose, there's exactly one plane that goes through those 3 points. Any 3 points you take in space, there is one and only one plane that goes through those 3 points, if they're non-collinear. They can't be collinear. The same way that if you take any 2 points that aren't copointer, so 2 points that aren't the same point in 2-dimensional space, then there's one and only one line that goes through those 2 points.
Mm-hmm.
That's the similarity. So pick any random 3 points of space that you want. If I can't draw a line through all those 3 points, then there's one and only one plane that goes through all 3 of those points. That's the second postulate. Third postulate. Each plane satisfies all the postulates for plane geometry. Duh. Postulate 4. So the one similar to this. So we said that any line we draw separates our plane into 2 sides, or into 3 sets. There's a set of points on this side of the line, there's a set of points on the line itself, and then there's a set of points on this side of the line, right? And what did it mean for one line to be on an opposite side? Or one point to be on an opposite side? If I said point P and point Q are on opposite sides of the line, what did that mean?
That there's an intersection.
That there exists a point, Z, I don't know, such that Z is between P and Q. There exists a point Z on the line such that Z is in between P and Q. So we've got a similar theorem now that says any plane separates space into 3 sets. The sets of points on one side of the plane, the sets of points on the plane, and the sets of points on the other side of the plane. So the plane divides space into 2 sides. And what does it mean for 2 points to be on opposite sides of the plane? That means that there exists some point on the plane between those 2 points. Does that make sense?
Yes.
And hopefully that makes intuitive sense, right? I could divide this room into two sides with a plane through it. So let's read exactly what it says. Each plane separates space. By this we mean that the set of points of space not on the plane consists of two subsets called the sides of the plane, with the following properties. If 2 points are in the same subset, then the segment joining them does not meet the plane. But if the 2 points are in different subsets, then the segment joining them does intersect the plane. Does that make sense? If 2 points are on the same side of the plane, here's the plane. If 2 points are on the same side of the plane, there's no point in the plane in between them. If you draw a segment from this point to this point, it doesn't intersect the plane. There's no point on the plane between them. Remember our definition for a segment? If I have a point A and a point B, what's a segment AB? It's the set of all the points between A and B. So if I can draw the segment, all the points between A and B, and it doesn't intersect the plane that's right here, then they're on the same side. If they're on opposite sides of the plane, then there is some point on the plane on their segment. There's some point on the plane in between the 2 points. Does that make sense?
Yeah.
Great. So now he tries to give those 4 postulates again in plain English. So the first postulate asserts that no plane fills up all the space, so that we have a geometry of more than 2 dimensions. That was a postulate about 4 points that aren't coplanar. Postulate 2 gives us a simple requirement for fixing a definite plane. That's one that says any 3 non-collinear points give us a unique plane. Postulate 3 states that our planes are as we want them to be from our study of plane geometry. In addition, this postulate relates congruent lines and angles in different planes. Did I not finish reading that postulate?
Furthermore, at the top of the page.
Oh, let's read postulate 3 one more time. Each plane satisfies all the postulates for plane geometry. In particular, the line joining 2 points of a plane lies in that plane. Furthermore, the postulates of congruence of segments and angles apply whether or not the segments and angles are in the same plane.
So right angle is a right angle, even if it's in a different plane.
Yeah, so a right angle on one plane is congruent to a right angle in another plane. What did we mean by angle congruence? Or what were our postulates about angle congruence? So let's pretend that I have a plane here and I had a plane here. And those 2 planes aren't the same points, right? And I have some angle here. Then, if I have some ray here, then there is only one angle I can draw on a particular side of this ray such that this angle is congruent to this angle. And that's true even when they're in different planes. That was the case when they're in the same planes. Now it's true when they're in different planes. Right? So that was, for example, one of our postulates about angles for congruence. So all our angle congruence postulates that we had are true regardless of whether or not our 2 angles are in the same plane or in different planes. So furthermore, take the supplement of this angle and the supplement of this angle, they're congruent. And we can say all the things that we can say about angles. Does that make sense?
Yeah.
So whether they're in the same plane or in different planes, our congruence theorems and postulates about angles still holds the same way. Okay. So that was postulate 3. Postulate 4 expresses the familiar fact that a wall between neighbors separates them. And postulate 4 was the one that a plane separates space.
That's the
into
only
2
one
sides.
that he actually put in plain English.
Plain English.
Or
It's the only one that didn't have plane in it. How's that plain English?
That means if you want to separate a room with someone, you shouldn't draw a line. You should draw a plane. Or else it only applies to things in the plane of a line.
Alright. So let's do some proofs in this new geometry. If a line L does not lie on a plane pi and has at least one point in pi, then L and pi have exactly 1 point in common. So what's that saying? It's saying, I am not an artist, so this is going to be tough. If I have a plane, and I have a line, and I know that the plane and the line have a point in common, but that the line does not lie in the plane, meaning not every point of the line is in the plane,
They have exactly one.
then they only have 1 point in common. So if the line and the plane intersect at 1 point, and they don't intersect at every point of the line, then they only intersect at 1 point. Does that make sense?
Mm-hmm.
How do we prove this? Prove it by way of contradiction.
And they intersect at 2 points.
So assume, by way of contradiction, so this is plane pi and this is line L. You don't like plane pi? Like
I thought he was-
apples in it or something? So assume, by way of contradiction, that L and pi intersect in at least one, and we'll let P be the name of their intersection, P.
2. This is a contradiction.
Right. So assume by way of contradiction that L and pi intersect at least 1 point
Oh,
other than P. Call it Q. So assume that there is some other point on the line, Q, that is also on that plane. 2. Then line PQ lies in pi. Right? Going way, way back to the beginning, 2 points defines a unique line that goes through those 2 points in a plane. Right? If I say that a line goes through, can't do it over there because camera can't catch it. If I say that a line goes through this point and this point, I am guaranteed that there's only one line that goes through both those points, and furthermore that that line lies in this plane. Because this was true in our planar geometry, right?
Mm-hmm.
So, then line PQ lies in pi and is unique. And is unique. Or in other words,
not listenable for contradictions.
then PQ is L.
Okay, why do it?
Why is that a contradiction? You probably have to read the theorem again because we didn't write it down there. So let's read the theorem one more time and see why this...
Because it lies on the plane pi.
Yeah! We're saying L lies on pi. We assume that L doesn't lie on pi, but goes through to 1 point. That's what we're given. We're given L intersects pi at 1 point, but L doesn't intersect pi at every point. That's what we were given. Then we said, is it possible that L intersects pi at more than 1 point? So we said, let's pretend it does intersect at more than 1 point. Well, if it does intersect it at more than 1 point, then it lies in pi and intersects it at every point, which doesn't work. So it must only intersect at 1 point. You see the logic?
Mm-hmm.
Okay. That's one example of a theorem. Theorem 2. There is a unique plane containing a given line and a point not on the line. there's a unique plane containing a line and a point not on the line. So let's make sure you understand this. If I draw this line here, and I take a point on Laura's nose, that point, I'm saying there's only one plane in existence that goes through that line and the point on Laura's nose. There's one and only one. That's what we need to prove. Okay? Now, rather than it being on Laura's nose, we're just going to draw it right here. How do I know that there is only one plane that contains this line and that point? How many points do we need to define a unique plane?
3.
3. How many points do we know that there are on a line? At least.
2.
So we know there's at least 2 points on a line.
Okay.
And we were given some point not on the line. That gives us a unique plane.
Oh.
Our postulate says that if we have 3 non-collinear points, there's one and only one plane that contains those 3 points. And the plane that contains these 2 points contains this line. Right? From our other theorem, if it contains more than one point, it contains all the points. Do you see that? Do we need to write it out, or do you understand it? You understand it? Explain it.
Okay. So the reason that that point and the line are on the same plane is because on a line you have 2 points. On a line you have 2 points, and every plane has at least 3 points that are not collinear. So the other point makes the last point for the 3 points, and it makes its own unique plane.
Good. The one thing that you didn't say in there that makes it better, you says 3 points give you a plane. It's 3 non-collinear points. Not only do they give you a plane, they give you one and only one plane.
I said unique.
You said it later.
Oh.
You're just concluding, therefore it's unique. But I think you understand. We're good. Okay. Next. There are infinitely many planes containing a given line. There are infinitely many planes containing a given line.
Yep.
So let's think about that. So I've got this line right here. How many planes contain that line?
Infinite.
Well, there's Donna's nose, there's Cole's nose, there's my nose.
So how can we prove that infinitely many planes contain this line?
Because there's infinite.
You just
many
test it.
points that you can round it, I guess.
Well, we know with 1 point and a line, we get a unique plane, right? And then how many points are on a line?
Infinite.
At least 2.
Infinite,
Oh.
right?
Yep.
So I know that there's at least 4 points in existence that aren't coplanar. 1, 2, 3, 4. Here's my 4th point.
I know that these 3 points make a plane.
So I'm guaranteed that there's these. Then, with this point, I can draw another line, that goes through this point. You see it? How many points are on a line?
Infinite.
Infinitely many. So then for every point on this line, I can take the plane that goes through that point and this line, and I get another plane.
Yep. I see it.
Wait, are you right? You can't be right. You're picking the wrong point to make a line through, I think. You gotta make a line through that other point. Otherwise, all those points are on the same plane. I think. Your point that you're picking gives you 3 distinct non-collinear points with the line included.
Every line. Oh, did I use this point? I meant to
Yeah.
use this point.
Yeah.
Sorry.
Oh.
That's what happens when I'm talking to you, not looking at me. Let's say that again. I have 4 points. I need all 4 of my points. So I do the line through these 2 points, and then the line through this point and this point, has infinitely many points on it. And now, for every point on this line, I could take that point and this line and get a plane that goes through this line. Do you see that?
Yeah.
That's what I meant to say. Sorry. I don't know what I said before because that's what I meant to say. You're saying I accidentally used one of these points again?
Yeah.
Yeah, that doesn't work because I can make a plane that goes through
It's a 1.
this line and this point, and it would go through all those points. It's going to be our next theorem, but basically we're saying two intersecting lines defines
Unique.
a unique plane as well. So I needed two lines that aren't intersecting. This line and then this line aren't intersecting. Okay. Anyways, so that's how you would prove that. Next theorem. There are infinitely many planes. No, we did that.
14.4.
There is a unique plane containing two intersecting lines. Okay, so let's think about that. How do we prove that? So we have two intersecting lines. We need to prove that there's a unique plane containing those.
Like 2 points.
Yeah, pick another point on this line. Pick another point on this line.
That's one plane.
How unique is that?
There's 3 points, which is one plane and only one plane containing these 3 points. Furthermore, since that plane contains 2 points of this line,
You
it
can
contains the
make
whole
another-
line. And since it contains 2 points of this line, it contains the whole line.
Oh, I see what we're doing.
So one and only one plane contains both these intersecting lines. Good? All right, what's next? If two distinct planes have at least one point in common, then they have precisely a line in common. Okay? This is really starting to challenge me. How do we demonstrate this?
We gotta teach class in VR.
Okay. Here's a plane, and then we're going to have a plane perpendicular to it, like this. Bam. You with me so far?
We'll boom.
So we got the whiteboard, and then this perpendicular one that goes through the whiteboard.
Mm-hmm.
And I know they intersect at least one point. Okay?
Yep.
I also know that a plane divides space into 3 sets. Right?
Okay.
The set of points on the plane, the set of points on one side of the plane, and the set of points on another side of the plane. Right? So pick one point on this side of the plane. Pick one point on this side of the plane, so that these 3 points aren't collinear. Right? Since they're on opposite sides of the plane, then there has to be a point on the plane in between these 2 points.
Oh.
That gives us 2 points. On
So there's 2 points where they intersect, so that gives us our line that we want.
Precisely one line. Why are we saying that's the only line?
If it was another line, then they're the same plane. So we know that they intersect at least 2 points. Now let's assume that they also intersected at a point that wasn't on that line. Then if they intersected here, then they intersected this line as well. Then they're the same plane because 2 intersecting lines defines a unique plane. So that forces them to be a plane. So if they're not the same plane, then they can't intersect in more than one line. So we just need to show that they intersect at least one line. Right? You understand how planes can't intersect in 2 lines? Because it forces it to be one plane at that point?
Right.
Okay. So I have to use a side postulate for that one. Okay, definition of a dihedral angle.
Or is it plane name?
Pi plus.
Pi plus 1 and pi plus 2.
Yeah. So a dihedral angle so pretend that this paper is one plane, this paper is another plane. Okay? You take all the sets of points on a particular side of both the planes, so it's like getting a ray. The same way that a ray was half a line, we're taking like a half plane Okay?
Okay.
So here's the line that they two planes intersect at, right?
Mm-hmm.
Take all the points on one side of it in this plane, all the points on the other side of it in this plane, which gives us our two almost rays. They're rays if you look at it perfectly, but otherwise they're half planes, right?
Mm-hmm.
A dihedral angle is a set of points on this side, on the same side of this plane as this plane, so all the points up here, and all the same side of this plane as this plane, so all the points over here. So it's all the points on these two planes for these two halves, or in between them. That's a dihedral angle. Did that make sense, what I just said?
Yeah.
Yeah, it's just a 3D version of what.
Wait, or in between.
Yeah. Oh, is it not or in between?
An angle doesn't include points in between. So dihedral.
Oh, no, that's right. Sorry.
But the interior is.
The interior is also. So let me read the definition now, exactly. The interior of a dihedral angle. Oh. Okay. So yeah, what I created, this was a dihedral angle. Just the paper itself is a dihedral angle. And then the interior of the dihedral angle is this. The same way that just an angle was a ray, right? There was an angle, it's the ray, and then this was the interior of the angle. The paper is a dihedral angle, imagining that the planes go off forever. And then this part is the interior of the dihedral angle. Does that make sense? So let's read it exactly now. So this is the definition of a dihedral angle. If two planes, namely pi1 and pi2, intersect in a line, these two intersected in a line, where that crease is, the bottom of the paper, the point. If two planes intersect in a line, let pi1 plus and pi2 plus be half planes of pi1 and pi2, determined by the line. So pi1 plus would be one of these halves, and pi2 plus would be the other half. So we're saying only take half of each plane. The set of all points in each half of the plane is called the dihedral angle. The line L is called the edge. So where the crease on this paper is the edge of the dihedral angle instead of the vertex. So instead of a vertex, now we have an edge. Instead of an angle, now we have a dihedral angle. Good?
Mm-hmm.
And then the half planes are called the faces of the angle. These were called the sides of the angle. This and this are called the faces of the angle. So instead of vertex, we have edge. Instead of side, we have face. Instead of angle, we have dihedral angle. Instead of it being composed of half lines, it's composed of half planes. Does that all make sense?
Yeah.
All right. And then the interior of the dihedral angle, with faces pi1 plus and pi2 plus, is a set of all points of space on the same side of pi2 plus as pi1 plus and pi1 plus as pi2 plus. So the interior is all the points in space on the same side of this plane as this plane. So what side of this plane is this on? It's up here. So that's all these points and all these points. Take the intersection of those. That's the interior. Good? Okay. Really wish I was a better artist. Okay, next definition. A line L is perpendicular to a plane, pi, if L intersects pi at a point P, and L is perpendicular to every line in pi that passes through P. So let's understand that. Here's a point P in this plane. Here's a line through P, here's a line through P, here's a line through P. Move P so it goes through those points. Here's another line. When is this perpendicular to the plane? Is it perpendicular right now?
Mm-mm.
Now? About like that, right?
Mm-hmm.
That's roughly when it's perpendicular. So here's what it's saying. A line through P is perpendicular to the plane if it's perpendicular to every line that passes through P. So it's perpendicular to this line, it's perpendicular to this line, it's perpendicular to this line. Does that make sense?
Yeah.
That's what we mean for a line to be perpendicular to a plane at a point P. So let's read it one more time. A line L is perpendicular to a plane pi if L intersects pi at a point P and L is perpendicular to every line in pi that passes through P. So this can't be perpendicular to this plane if it doesn't intersect it at a point, right?
Mm-hmm.
If it lies in it instead of intersecting at one point, nope, can't be perpendicular to the plane. So it has to intersect at one point, and it has to be perpendicular to every line in the plane that goes through that point. Good?
Mm-hmm.
Okay. Theorem. If a line L is perpendicular to two intersecting lines, then it is perpendicular to the plane containing the lines. That one's going to be kind of messy to prove. Whew. Yeah, you see in figure 14-15?
Mm-hmm.
That's the figure he's using to show it. Let's go over the proof idea, and I won't bother trying to go through the proof because I don't dare try and draw that. So, the proof idea is this. If I know that this line is perpendicular to these two lines, then I show that that is enough information so that if I add some other third line, this would also be perpendicular to that third line. Okay? So that's the proof idea. And it uses congruent triangles
It says-
going into three-dimensional space, which I don't think I can draw.
Then it is perpendicular to the plane containing the lines.
Right. So we say, look, it starts out perpendicular to two lines, then add any arbitrary line you want, and it's also perpendicular to that line. Therefore, it's perpendicular to every line that goes through P.
And then that makes it perpendicular to the plane.
What does it mean to be perpendicular to the plane? Definition. A line is perpendicular to the plane if it's perpendicular to every line that passes through that point where it intersects the plane.
Okay.
So we start out with it's perpendicular to 2, then we say any other line you add, it's also perpendicular to that line.
Yeah.
Therefore, it's perpendicular to the plane. Does that make sense?
Mm-hmm.
Okay.
I don't know why he had to do so much.
Well, it's not so much, it's just he has to work in three-dimensional space.
3, 4 triangles.
And then there's exactly one plane perpendicular to a line and containing a point not on the line. So if I take this line and I pick a point not on the line, so here's my point not on the line, here's my line. I'm saying that there's only one plane that goes through this point that's perpendicular to this line. Right? And that's the whiteboard. There's no other plane I can make go through this point that would be perpendicular to my yardstick. Good?
Yep.
That's what that one's saying. If two lines are perpendicular to the same plane, they are parallel. And that just follows from our congruence seems not caring about what plane they're in. Perpendicular lines are, I mean, we can go over the idea of that one real quick. So, make sure you understand what's
Did
saying.
you skip 17 or 14.7?
Did I?
There's exactly one plane perpendicular
It's the same
to a
as
line
the
at
one
the
you
point.
said, except that point is ongoing.
Oh. There's exactly one plane perpendicular to a line at a point on the line. So, pick a point on my line, namely the end of my yardstick. And here's my line. There's only one plane that goes through the end of my yardstick, perpendicular to my yardstick. Any other plane I draw that goes through the end of my yardstick isn't going to be perpendicular. It's going to have to be slanted some. Does that make sense?
Yeah.
Okay. Now the next one says, if two lines are perpendicular to a plane, so I have this one coming out right here and this one coming out right here, then those two lines are parallel to each other. And that's easy. We know that they both, so this one goes through and it intersects at this point, this one goes through and it intersects at this point, so we have a line here. Since they're both perpendicular to this line, then they're parallel. The same way that two lines inside the plane perpendicular to that line are parallel. Good?
Mm-hmm.
Wait.
I don't understand what you're saying with that.
So imagine now, so I know that this and this are parallel.
Okay.
So imagine now I grabbed them and pulled them out of the line where it's now they're perpendicular this way instead of this way.
Okay.
They're still parallel. They never intersect.
That's what I'm saying.
Okay. They don't even have to be perpendicular to the plane. So it's not meant to do that.
Oh, I see what you're saying.
They can be in parallel planes. That's all that matters. But
Yeah, they'd be in parallel planes. So let's see how we can
That's
ensure
true.
that they're actually parallel, and that they also would lie in the same plane.
well, they do lie in the same. Do they?
No.
No. Okay.
So how do we make sure that they lie in the same
Well, you
plane?
use your
Well,
other theorems,
First one must.
right? So
It says first one must show that two lines are in
if
one
two lines
plane.
are perpendicular to the same plane, they are parallel. They are parallel lines. We don't care.
If two lines are perpendicular to the same
Oh.
plane, right?
But
But if
we
I can
do
show that
that.
those two lines lie in the same plane,
Well, that's a given. It's given that they're perpendicular to that plane. How do we know they're parallel? Because they're parallel to all lines on that plane.
Okay.
You mean they're perpendicular?
So the thing we're trying to make
They're-
is a given
so we know that I have two lines perpendicular
to that plane, not
to this plane.
Yeah. So
How do I know that they're parallel to each other?
Because they lie in the same plane.
because they're perpendicular to every line on that plane.
They're perpendicular to every line on this plane. That doesn't mean that they're parallel to each other. The only way I can show that they're parallel to each other is that they lie in the same plane. In other words, I could have a plane coming out here.
No, because these two lines are parallel and they don't lie on the same plane.
Why are they parallel?
if they're
I think
planes are
parallel implies in the same plane.
Nuh-uh. Look, you have 2 planes. Any lines on those two, you have 2 parallel planes. Any lines on those 2 parallel planes are parallel lines, even though the lines could lie on different planes.
See, and I don't think that they are.
There's no way you could draw a I need my VR.
I think that they have to be coplanar lines
Nuh-uh.
to be parallel. They have to be coplanar and not
you're saying the
intersecting.
definition of parallel?
Yeah.
That's dumb.
No, that's good. I don't want a line that goes like this and a line that goes like this to be considered parallel. Just because they never intersect.
Well, their planes aren't parallel. I'm saying, as long as their planes are parallel, they're parallel.
A line doesn't have a plane. There's an infinite number of planes that go through a line. For any two lines you give me, I could draw plane theorems that are parallel.
Right.
Could I? I don't know if that's true.
You could probably,
Yeah.
Probably, I don't know.
unless the line.
But I do know that
Unless the lines intersect.
if we're going to say they're parallel, we have to be able to say they're coplanar.
Okay.
So,
If two lines are perpendicular to the same plane, they are parallel.
yeah. So we need to say they're coplanar. So we have two lines coming out. They're
Wow.
perpendicular to every line in that plane, sure.
And then we make a plane with the line containing the 2 points.
Those 2 points, yeah. And then what other
Any
point?
other point on either line.
How do I, so I get this, and a point here on this line. How do I know it contains another point on this line?
So, holy cow, this is hard. So you have a plane. You have that, and that. And you know there's exactly one plane containing those 3 points. Fudge. Wait. What about one of those 2 points on the whiteboard and then points on either of the lines? What is that?
Yeah, and that's even their hint. Hint, first one must show that the two lines are in one plane.
And we can do that by picking that point on this line, and another point on this line. That's one plane, right?
Then we're only guaranteed one line goes through it. How do we get that the other line goes through it?
No, that's a plane containing both. Oh. How do I know?
How do you know that that plane contains both of them?
Because it contains a point on this line. Okay, you know that there's one plane. I'm gonna walk up that.
Let's just draw like this. Pretend we're in 3 dimensions for a second.
That's
So
harder.
brown is my plane.
Okay. So we're assuming that these two are perpendicular.
So I know that this is perpendicular to this, and this is perpendicular to this.
And like that.
Yeah.
Okay. So point here, point there, point there.
So you're saying this point,
One unique plane.
this point, and this point.
One unique plane contains those 3 points.
Uh-huh.
Okay. Now do the same thing here. Point there, point there, point there.
Uh-huh.
We know that if a plane contains this line and this line, and it contains this line and this line, then those 2 lines have to be contained by that same plane.
Good. Wonderful. Yeah, that logic works. So let's go over exactly what he was saying. So first thing we need to show is that these 2 lines are in the same plane. How did we do that? He was saying, look at this point, this point, and this point.
One unique plane.
There's one and only one point that contains this point, this point, this point, which then contains this line and this line.
Mm-hmm.
2 lines define a unique plane. So there's one and only one plane containing this line and this line. Now, your proof still doesn't work.
Because
Just because I have a plane that contains this and this, and a plane that contains this and this, does not mean these 2 are in the same plane.
that and that, that and that. Do we need to make a third one? That. Okay. Yeah. That and that.
Hmm.
Okay, there's one. I need to read it. Exactly one plane perpendicular to a line at a point of the line. 2 lines are perpendicular to the same plane. There is exactly one plane perpendicular to a line at a point of the line.
Ah,
There is exactly one
there is
plane
exactly one plane.
perpendicular to a line at a point. And okay.
There's exactly one plane. Say that again.
There's exactly one plane perpendicular to a line and a point of the line.
There's
One
exactly
plane.
one plane perpendicular to a line.
To a line and a point of
Oh,
the
but
line.
that's not what we have. exactly one plane perpendicular to a line and a point on the line. There's exactly one plane perpendicular to the line and a point on the line.
You have two lines. The line L is perpendicular to two intersecting lines. Then it is perpendicular to a plane containing the lines. Okay? So, reverse that. We have a plane perpendicular. We have a line perpendicular. Then it is perpendicular to the plane containing the lines. So we have that a line L is perpendicular to two intersecting lines. All that gives us is another intersecting line to either of those red lines on the red.
Well, here's what I'm thinking. So we have this plane. We take some point on the line and draw a line through it, doesn't matter, on this plane. There's exactly one plane perpendicular to a line in this plane at that point, or at that point, or at that point.
Okay. How do we know that those bottom 2 points are on that perpendicular plane? Because for every line.
Because every line through that point.
Yeah, every line. But how do we know
Yeah,
that
that's
the
still a
one
weird
plane
connection.
contains both of those lines? Because it's in a definition.
Well, let's move forward. I don't see it, obviously, and I'd have to think more about it to come up with something. I might have to break it down to triangles and showing that if we take the plane that contains this line, this point, and take some other point perpendicular to the plane, then it also is on that line, or in that plane. I don't know. I have to think about more. All right. Two lines are called skew if they do not lie in one plane. Two planes are called parallel if they do not intersect. So two lines are skew if they do not lie in one plane. Does that make sense? So if I have this line and this line, these two lines are skew. There's no plane that you can make that contains this line and this line. And then two planes are parallel if they don't intersect. That one makes perfect sense. Through a point P, not in a plane pi, there's exactly one plane parallel to pi. This is going to fall from the other one. The proof that we can figure out. So, if I have, let me get that one more time. Through a point P, not on a plane pi, there's exactly one plane parallel to pi. So if I have, here's my plane, here's my point. There's only one plane that I can make through this point parallel to this plane. Right?
Right.
That make intuitive sense?
Mm-hmm.
If you skew it just a teeny bit, it's eventually going to intersect the plane. Two planes perpendicular to the same line are parallel. So if I have this line is perpendicular to this plane, and I have another plane right here perpendicular to this line, then this plane and this plane are parallel. Does that make sense? If this is a 90-degree angle to here, and then I got my plane here, and it's another 90-degree angle, those two planes never intersect. It's like two straight walls.
Yep.
Two straight walls are parallel to each other because any line you draw from one wall to the next, it's going to be perpendicular to both those walls. Those walls are built 90-degree angles. Kind of out of time, aren't we?
There's 24 theorems, so we're barely halfway.
Yeah, the reason there's so many is because he doesn't prove them. He just mentions them. So you can just read through those theorems. I'm not going to keep covering them since we're not proving them in class. I don't want to take the time to prove them. So you can finish reading through those. We won't bother finishing with space geometry. Next class we will go over analytical geometry and then philosophy of mathematics. Philosophy of mathematics is a really short chapter, just a couple pages long. And that part of the class there's no proofs or anything. It's just a discussion of the philosophy of mathematics. So I strongly recommend you read it, and then we'll just have a conversation about it. Does that make sense what I'm saying?
Yeah.
There's nothing to prove about it. There's no problems. It's just talking about math in general and its relation to other fields. And I can point out some of the misconceptions that the author has about philosophy along the way.
That sounds funny.
No. Love of wisdom. That's pretty cool.
That's the definition of philosophy.
Philosophy.
Love of wisdom. To make it make more sense in terms of how we think. It would be love of knowledge. So the Greeks called any field whose end was knowledge a science, and grouping all those fields together is what they call the study of philosophy. And so, for example, physics, what we now call physics, the Greeks would have called natural philosophy. That's the study of the natural world. That's just one example.
So if I'm a lover of wisdom, I'm a philosopher.
Well, the Greeks would argue that if you're a lover of wisdom, that's demonstrated in your actions. And so that would mean that you're actively pursuing, so I should be careful how I say this. I'm only familiar with Socrates, Plato, and Aristotle. And so I only know how they would use the word. And for you to call yourself a philosopher in their eyes means that you are actively seeking out the good, the true, and the beautiful. Now, they operate on the premise that the good, the true, and the beautiful are objective, meaning your opinion doesn't mean squat. What's true is what's true, whether you believe it or not. What's good is what's good, whether you think it or not. What's beautiful is what's beautiful, whether you like it or not. So your opinion about what's beautiful is irrelevant. All we can hope to do is try and line it up with what is actually beautiful to the best of our ability. What you think is good is irrelevant. All you can hope to do is line your opinion up with what's actually good to the best of your ability.
Because you don't know. Because your opinion does not matter.
Well, when I say your opinion doesn't matter, what I mean is your opinion doesn't change the reality of it. Just because everyone on planet Earth thinks 1 + 1 is 3 does not make it 3. What's true is true, independent of opinions. Just because everyone on planet Earth thinks murdering is okay doesn't make murdering okay. It's either evil or it's good, regardless of what people think. Just because everyone on Earth thinks Mona Lisa is beautiful doesn't necessarily make it beautiful. It either is or it isn't.
But then you have to come up with definitions and stuff like that.
You don't always have to come up with definitions. We just went over in this class what you need if you're going to develop a system, a logically consistent system. You need undefined terms, which are given meaning through axioms, and then you have definitions, and then you have theorems.
Well, that's what I meant by definitions. You have to have the base.
Well,
A certain base.
your definitions come from undefined terms. You have undefined terms. You have axioms or postulates.
Yep.
You have defined terms, and then you have theorems that you then prove from that stuff. But no, it's based in something. You take at some root an assumption. For example, you didn't prove that if a statement's not true, it's false. You never proved that. Why are you going around saying that? It's an assumption that you make in the field of logic.
Yeah, but how can you truly say, or how can we ever find what is truly beautiful if we don't? I'm just confused.
What's your definition of truth? You go around saying things are true all the time. What's your definition of true?
I don't have one.
Yeah, we never once said our definition of true. We just said right out the door, statement is either true or false. True and false were undefined terms. And we said if it's not true, then it's false. If it's not false, then it's true. And we continued going on with our lives, never defining what true was and what false was. You can't define everything.
Yeah.
You have to start somewhere.
It's like congruent, that's my favorite example of that. They don't say congruent is this, they say congruent. And then say, oh, here's a situation where something's congruent, here's a situation where something's congruent.
Right. Through your postulates, you give meaning to the word. So they say something along the lines of beauty is objective. That's one of the ways that they're giving meaning to what they mean by beauty. Your opinion about it doesn't matter. It's objective. It's one of their postulates. Premises that they operate on. Does that make sense?
Mm-hmm.
So you don't have to have definitions to start talking about these things. That's a misconception. We never once defined what a point was. We never once defined what a line was. We never once defined what a plane was. We never once defined what space was.
We just said if this and that.
No. We said a line has at least 2 points.
Oh.
Well, what's a line? I'm not answering that. Not once did I claim that I have a definition for what a line is. But a line contains at least 2 points. What's beauty? I never said I know what beauty is. But beauty is objective. I don't have my definition, but I can tell you properties of it. I don't have my definition of a line, but I can tell you properties of it.
Okay.
And they can go on giving their properties of what the meaning is captured by these words without an actual definition for what the word is. And that's a perfectly valid way to develop a system. We just did it.
It's the only way
Yeah, that's a hard thing to say. Because one of the craziest things in math, what's his name? I never know how to pronounce his name because it's a German name. It's got the 2 O's with the dots above it. But it's like Gödel or something like that. For some reason, it's not Gödel. It's like Gödel. But he has a proof that any system, any logic system you have built the way that we're talking about with axioms and postulates, is either incomplete, meaning it doesn't prove everything that can be proven, or it contains a contradiction. So it is impossible to have a perfectly complete system. We'll say math for now because math it all reduces to the same thing. So we know that it is impossible for us to have some set of postulates from which we can prove all of mathematics. And if we do get one, then we have a contradiction in it.
You proved that?
Yes. Now, it's a hard thing to understand how he proves it because he goes outside of mathematics to talk about mathematics using mathematics. Has to do with encoding statements with prime numbers. But how he does it is irrelevant and well beyond the scope of this class. The point is, that's been proven.
So what?
It's crazy.
There's things that are true that it can't prove are true.
Oh. There are things that are true that cannot be proven
To be true.
in that system.
In that system. And if the system can then say that everything is true that is actually true, it will also say something that's true is also false. And it will have contradiction.
There are things that are true that cannot be proven. It's incomplete.
And it has to do with creating logical contradictions like, what's a really...
Yeah, I feel like I can kind of see how the proof would go.
You end up creating scenarios like, one of the famous one is, well, I won't say it that way. I'll use the more, my words will leave me. I'll just tell you, I can't say anything right now. Okay, so there's a village with a population of males, and it is given that every male in this population is shaven. Okay?
Okay.
There's a barber in the population, and it is given that the barber only shaves males who don't shave themselves.
Okay.
And he shaves every male that doesn't shave himself. So he shaves every male that doesn't shave himself.
And it doesn't shave any male that does.
He doesn't shave any male that does shave themselves. Every male is clean shaven. So let's pretend that these are our postulates, and now we want to ask questions about this population. Okay? A simple question we might want to ask is, does the barber shave himself? Think about it. If the barber shaves himself, then the barber only shaves people who don't shave themselves, so the barber doesn't shave himself. But then the barber shaves everyone that doesn't shave themselves, so the barber shaves himself. And so you create this paradox. Any statement that's true, you can also show as false. And if you show it's false, you can also show it's true.
That is so cool.
It's an inconsistent system. That is an inconsistent set of postulates that A, everyone in the village is shaven, B, the barber shaves everyone who doesn't shave themselves and only shaves everyone who doesn't shave themselves, C, there's a barber in the population. So if that was our set of postulates, it's an inconsistent system. It proves some statement both true and false. And you can do similar types of tricks with talking about statements in general.
Right, you could assign logic functions to them.
Well, I'm trying to think of an example really quick.
I should try that.
It's stuff along the lines of I've got an example on the tip of my tongue, and it's just escaping me barely. I can't think of it. Shoot. I keep wanting to give you some, but I'm afraid if I give you some, I'll just confuse you more than I help you, because I can't see where it ends.
That I understood the first one.
Yeah, the first one, that gives you an idea of the types of inconsistent systems that are kind of easy to develop.
Wow. What makes that inconsistent? And then break that down to the fundamentals. Right?
Well, you'd get to same type of interesting questions in computer science. So if you ever take what's called computation theory, one of the things you're interested in is a set of problems that can be solved by a Turing machine. And what we call it is the language it can recognize and the types of questions that it can answer. And basically, a Turing machine can answer anything that you could write an algorithm to come up with an answer for. And there's no proof that you can do anything that Turing machine can. So right now we don't know whether or not a human and a Turing machine are logically equivalent. Whether there's any problem a human can solve that a Turing machine can't, or whether there's any problem that a Turing machine can solve. Well, obviously, anything a Turing machine can solve, a human can solve, because a human can create a Turing machine can solve the problem. So we don't know if there's any problem that a human can solve that a Turing machine can't solve. Anyways, but the language that it recognizes, a set of problems that it can answer, are severely limited. Let me give you... I can't give you the acceptance problem that quick. Or the halting problem is one way that's shown.
Yeah, but how are they severely limited?
For example, okay, I'll just tell you what it is, and you might not believe the result. We know it's impossible to create a Turing machine that can look at a program, regardless of what the program is, and determine whether or not it's going to crash. So there's no guaranteed method that if you write a program, I can have a Turing machine look at that program and know whether or not it's going to crash. It has to do with predicting the future. I could do the same thing with predicting the future. I can prove that it's logically impossible for you to create a machine that can always predict the future.
Gonna crash. So gonna crash while it's running. The only way for the computer to know is it literally runs the program and crashes it, right?
Well, no, it can simulate a program that runs a computer.
Oh, yeah.
To see if it crashes.
Okay, that's where I connected to the future. Oh, that's so funny.
And to see a proof of that is
That's
actually
a simulation.
really simple. Every single one of you guys could understand it. If you went onto YouTube and said proof of the halting problem, you would understand the proof completely. It's a really, really simple thought experiment that they take you through. It's just, I can't do it. It helps when you have visual aids that I don't have.
Stop. Oh.
Yeah, halt meaning it crashes running the program. Determine if the program halts, gets stuck in an infinite loop. Programmers understand what I'm saying, but you don't need to understand programming at all to understand this problem. And so, it's even one of the simplest questions that you would want to ask about a program. Will this crash? We can't even answer that.
But
There are particular cases where we can answer it. No, you can answer it for particular cases.
Yeah.
But can you answer in general? Is there some surefire way that no matter what program I give you to run, you can determine whether or not it will run?
Can the computer can do it in particular cases. That's why I get warnings when I'm coding.
That's why you get warnings and errors when you're coding, yes. So it can handle particular cases. So that's what you need to understand. It's not saying that it can never determine when something's going to crash. It's saying it can't always determine when something's going to crash. It's not saying that we can never predict the future. It's saying that we can't always predict the future. That's what it is logically equivalent to saying. And so there's a bunch of questions if you can continue in computer science. We're done, by the way. You guys can go if you want. There's